Hello everyone, welcome to ECE 6520. Today is our lecture number 14. Alright, so in this lecture, we're going to continue talking about our homework 2 and finish it. Okay, so let's get started. So in the last lecture, we covered until problem, problem 4.3, right? So now let's start from this problem. So in this problem, we need to argue that for any distribution on the shuffle operation T and any distribution on the card position X, such that, so after shuffling, then the entropy can be increased, right? Okay, and if X and T are independent, right? So the goal is to explain each steps, right? Okay, so let's try to do that. Okay. 4.3. So the first step is that, so this guy has to be larger than or equal to this one, right? So this is pretty obvious because, so we're doing conditioning, right? So conditioning will reduce entropy. So the first one is the conditioning. Reduces entropy, right? The second step is as follows. So they argue that this equals to, so we take an inverse operation of the shuffling, and then on Tx and the given T. Okay, so the reason this is equal is that, so this operation, the T inverse, so this is known when T is given, right? And it's an inverse operation, right? It's inversible in T is given, and T is inversible. Therefore, so T inverse doesn't change the entropy, right? Okay, we know that, and then so we can actually do the inverse, right? The inverse exists, therefore it doesn't change the entropy. And the next step is that this guy basically equals to X given T, right? So the reason of this is that the inverse operation on the shuffle operation, so that is basically equals to 1, right? So it's inversible. And then next is that this equals to X, right? The reason of that is we assume X and the T are independent. Therefore, condition on T or we don't condition on T, the entropy will not be changed. Okay, then that will be the answer of this problem. Okay, so now let's see our next one. So our next problem is 4.6. So which is this one. So in this problem, for a stationary stochastic process, x1 to xn, this condition is very important, right? And then we're going to show this inequality and this inequality. Okay, so basically, so this inequality gives an upper bound of that, and here we have a lower bound for this quantity, right? Now let's see how we can show that. Okay, so this is problem 4.6, and for part A. Okay, so for part A, we need to manipulate on this part. Okay, so now let's see how can I do that. So let's write it down, x1 till xn over n. Okay, so normally when we get this, so the first step is that because here we need something about n minus 1, right? So therefore, we may want to use chain rule to make this term just appear, right? So by using the chain rule of entropy, so what we can get is that, so we can have this term x1 till xn minus 1, right? This is the term that we want. And then we have another term which is xn given from x1 to xn minus 1, right? Okay, so now we have this term here, which is nice, right? But so we somehow need to manipulate this term to get something similar, maybe, right? So let's see how can we so this term is our focus, right? So let's see how can we manipulate this term, right? So let's see. So because x, so the sequence of x is a stationary stochastic process, therefore we have shown that this guy given xn minus 1, so that will be less than or equal to hxi given xi minus 1, where I is from I till n. So this is from the stationary property, right? So I've shown this before. Okay, so this is because the stationarity okay, from the stationarity you can show, yeah, because as I increases, so that will be a decreasing function, right? So we know that. Okay, so now given that, so this is for each I, right? So therefore, let's do a summation of I from 1 to n minus 1, right? If we do that, then each of the term will be bigger than this guy, right? So it means that we need to do a summation from I from 1 to n minus 1. That will be less than or equal to, so this is from here, right? Minus 1. Okay, so very good. And the next step is that we can get, so on the left hand side, so this every term here is the same, so we have n minus 1 here, right? Okay, so now let's see on the left hand side, so what that is, right? So this is, if we write this out, it'll be like hx1 plus hx2 given x1 plus until hx n minus 1 given xn plus xn given xn minus 1, right? So this is exactly the chain rule, right, of the joint entropy of from x1 to xn minus 1, right? Okay, so maybe we don't have much space here. Maybe we can write it like this. So this guy is exactly equals to h x1 to xn, right? That is the definition of a chain rule. Okay, so now let's see. So given that, what we can get is as follows, right? So n minus 1 h xn given xn minus 1, that equals to h x1 till xn minus 1, which is something that we want, right? So this means that, remember, so now we're trying to bound this term, right? So we need to find the upper bound for that, right? So this is the follows, right? So this upper bound is less than or equal to this. Okay, so now we plug everything in this equation, right? So now this guy is less than 1 over n of this plus what we just computed here, right? So now we can obtain that hxn1 till xn over n, that is less than 1 over n, hx1 till xn minus 1 plus this guy, right? So that is 1 over n minus 1 times hx1 till xn minus 1, right? And that, now let's compute what that is 1 over n, and then we have n minus 1, and upstairs we have n minus 1 hx1 till xn minus 1 plus 1 times hx1 till xn minus 1, right? Therefore, it's equal to n minus 1. And upstairs, here's n minus 1, here's 1. So I have n times hx1 till xn minus 1, that equals to this, n minus 1, right? And you can see that this together is exactly what we want to show, right? Maybe I want to use another color here. So let's try to use red. So this guy is basically less than or equal to this guy, right? So now we finished the proof of this part. Okay, so let's see the next one. So for part B, now we need to show a lower bound of that, right? Let's see how we can do that. So let's change color back. So here, what we get is that we want to manipulate this guy, right? So because we want to show this is bigger than n multiply this one, right? Okay. So again, in order to make this guy appear, then we use the chain rule, right? So that is equals to h, let's see, 1 to n minus 1, right? So xn given xn to xn minus 1, right? And then we add what? Oh, sorry, we need to hxn till xn minus 1, we add hxn given xn minus 1, right? Now, what we want is a lower bound for the entire term, right? And recall this guy, right? Maybe you give a name for this, let's call this star, right? So here, from this one, we can see we can obtain a lower bound for this guy from this formula that we derived before, right? So maybe let's try that. So this is bigger than or equal to, so here's by using star, right? Then we get, so we move this n minus 1 to the other side, we have n minus 1 times, and add this, and you can see that this at that we have hxn given xn minus 1, so which is exactly what we want here, right? So now we finished the proof of part B, right? Okay, great. So now let's take a look at our next question. So our next question should be problem 4.7. Okay, so this is just a straightforward computation of the entropy rate for a Markov chain, right? So the first part is that find the entropy rate of the two-state Markov chain with the transition probability like that. Okay, very good. So in order to compute, yeah, maybe, okay, that's 4.7. Okay, so in order to compute the stationary distribution, right, which is, let's maybe recall, so the stationary, I mean the entropy rate basically equals to this guy for Markov chain. Since the Markov chain has a stationary distribution, so basically what we can have is something like that, right? And in order to compute this guy, so we know that we need the stationary joint distribution for the states, right? Therefore, so now in order to compute this guy, so the question becomes compute the stationary distribution of the Markov chain, right? So which is the result given by this transition probability, right? So now let's try to compute the stationary distribution of the Markov chain, right? So let pi denote the stationary distribution. Okay, and now what we can have is this equality, right? So pi times p equals to pi, right? And the other condition is that pi 0 plus pi 1, that is 1. Okay, so basically it means that we need to solve the following equation, right? It's 1 minus p 0 1, p 0 1, and p 1 0, 1 minus p 1 0, right? That equals to pi 0, pi 1. Okay, and together with this condition, right? Okay, so yeah, you can solve this equations. Therefore, what you can get is that pi 0. So I will not solve it here, but just it should be pretty straightforward computation. So you could get the stationary distribution is something like this, p01, and also pi 1 equals to p01 equal divided by p0 plus p10 and p01, right? Okay, so given this, the next step is to compute the joint distribution of all the states, right? So I have 4 cases, or p0, p0, or p01, we have p10, right? And also p10, and also we have p11, right? So now let's compute it one by one. So p00 is nothing but p0 given 0 times pi 0, right? So that is what? That is, so p00 equals to 1 minus p01, right? So that equals to 1 minus p01 multiply pi 0, which is this guy, p10 over p10 plus p10 plus p01. Then, okay, that'll be it, right? And similarly, you can actually compute everything with the same approach, right? So it turns out that these two guys are the same, right? Both of them equals to this guy. Okay, and lastly, so this equals to p11 times pi 1 equals to 1 minus p10 multiplied p01 over p10 plus p01, right? Okay, so now we have all the stationary distribution. Therefore, we can start our computation, right? So what we're going to do is we're going to continue this computation here, right? So we want to compute the conditional entropy of px1, px2 given conditional entropy of hx2 given x1, right? Okay, so this is equals to, we have all the x1, x0, and x1, and then p x0, p x1 log p, so x, yeah, this should be px1 x0, right? So px1 given x0, right? Or okay, so now we just plug everything in here, right? So the first term is basically this guy, right? So that is 1 minus p01 times p10 over p01 plus p10 log 1 minus p01. So that's the first term. And the second and third term is, we just add one by one, right? It's p01 times p10 over this log p01. And the next one is, so outside is the same, right? Because they have the same joint probability, but inside is different, right? It's log p10, and the last term is p01, 1 minus p10 times p01 over p01 plus p10 log 1 minus p10. Okay, and then we're done, right? So of course you can somehow combine this and that, right? Because they have the same constant here. We can see this is log, so we can maybe combine this, right? So maybe this and that. So we can get p01, p10 over p01 plus p10 log p01, p10, right? So we can somehow combine these two terms. All right, very good. And now let's see the second question. Part B is, what value of p01 and p10 to maximize the entropy rate? Okay. let's see how we can think about this problem, right? So from A, what we get is the entropy rate equals to hx1 given x0, right? So how can we maximize this guy, right? So we know this guy will be maximized when so x1 and x0 are independent, right? And since we know we only have two states, right? So the maximum value of this guy would be equals to 1, right? So therefore that will be our solution, right? So what we want is that so x1 has a uniform distribution, and x1 and x2 are independent statistically, right? So given that, we can see this will be achieved with p01 equals to p10 is half, so everything is uniform, right? And also, so from here we can get basically pi 0 equals to pi 1 is half, and also x1 and x2 are independent. Okay, great. Okay, let's see the next one. So the next part C is find the entropy rate of the two-state Markov chain with transition matrix, this one. So this is nothing but because we have the general form of the entropy rate, right? So we just need to plug everything in, right? So P01 equals to P and P10 equals to 1, right? So this is pretty straightforward. So we have P01 equals to P and P10 equals to 1, right? From here we can get pi 0 is 1 over 1 plus P, and the pi 1 is P over 1 plus P, right? Given that, so we just use the formula that we computed in part A, we can get this guy equals to what? So you can see that, so basically if P10 equals to 1, right? So this guy will disappear, and this guy will disappear. We only have the first two terms left, right? So then we can get this is nothing but 1 minus P, 1 plus P, log 1 minus P, and plus P, right? So if we take this negative 1 over, maybe we just take 1 over 1 plus P out, then we have negative 1 minus P log 1 minus P minus P log P, right? So if you still remember, this is nothing but the binary entropy function H2P, right? So that equals nothing but H2P over 1 plus P, okay? So that is for part C. And for part D, we need to find the maximum entropy rate of the Markov chain of part C, right? So to maximize this entropy rate, we expect that the maximizing value of P should be less than half, since 0 state permits more information to be generated than the 1 state, right? So this is like more uncertain compared to this one, right? Because we know if we start at 1, then we'll get to 0 for sure. Okay, very good. So now let's see how can we maximize this entropy, right? Part D. So this is nothing but, so now we know the analytical equation for this one, right? So it's nothing but a derivative of this guy with respect to P, and then we can obtain the result, right? So let's see how we can do the derivative of this guy. So that is, you need to recall your calculus, right? So yeah, we may, yeah. Okay, so maybe we write this as like something like this, 1 plus P, and then upstairs is this, right? So it's a fraction, right? So in order to do the derivative, so basically what we do here is that take the negative sign out, and then when you square the bottom, right, and then on the top, so what we need to do is that we need to do a derivative of this guy and multiply this minus this guy multiply the derivative of this guy, right? So this is what we're doing. So let's see, the first one is we don't change it, 1 plus p, and then we do the derivative of inside, right? And let's see what we can get. So here for simplicity, we just assume all the log is log, right? So we don't have additional constant to make our life troublesome. So this is what we got. Add 1 plus minus p, 1 minus p, and times -1 plus. So you can compute it on your own, right? So this is a step that I computed on my own, right? And the second one is relatively easy. Just copy this. Okay, right, hope it's clear. Okay, very good. Okay, so now let's do some simplification here. So with something that we can cancel it. So we have 1 plus p squared here, and upstairs we have -1 plus p, and you can see that here we have a -1, here we have a +1, so this one can be cancelled, and inside we have this guy, right, and then minus. Okay, all right, so now we just do some combination, right? Just try to make our life easier. In the end, eventually, so what we're going to get is something like this: 2 log 1 minus p minus log p, so that is 1 plus p squared, and log 1 minus p squared over p, right? That equals to 0. Okay, so in order to make that equal to 0, so what we need is the upstairs, the numerator equals to 0. That means 1 minus p squared over p, that is 1, right? And now you can solve it like p squared minus 3p plus 1 equals 0, right? So now in the formula to solve this quadratic function, you're going to get p equals to 3 plus minus square root of 5 over 2. And then we know p is less than 1, therefore, since p is less than 1, we know p equals to 3 minus square root of 5 over 2. Okay, that's now equal to 1. Okay, therefore, now we know the value of p, so we can plug p in to get the entropy equals to 0.6694 bits. Okay, that is for our part. So this is for part D, right? And so let's see for part E. Yeah, this is a little bit more complicated. Okay, here we let nt to be the number of allowable state sequence of length t for the Markov chain part C, right? So this guy. Okay, so now we need to find nt and compute this value, right? So now let's see how we can compute it. Okay, so basically, so the best way to find the relationship between nt and nt minus 1 and nt minus 2 is basically to illustrate from scratch and see the rules, right? So here you can see that when at first time slot t is 1, then we can see that there are like 2 states from 0 and 1, right? Okay, therefore nt1 is 2. And for nt2, let's see what is that. So nt2, we see, let's see, from here, we can see that, so from 0 can go to 1, and 0 and 1, but from 1, we can only go to 1, right? We cannot go to, we can only go to 0, right? So we cannot go to 1, right? Therefore, so here we can see from 0, we can go to 0, 1, and 0, 0, but from 1, we can only go to 0, right? There's only one state for the next state. Therefore, n2 is 3, right? And let's see how about N3. So N3, so similarly, we can see that from here, so from 1 we can only go to 0, but from 0 we can go to 0, 0, 1 and 0, 0, 0. And here, yeah, so here should be 1, 0, right? And here, because it's a 0 stage, right, we can go to 0, 1, 0, 0 and 1, 0, 1 and so on. Right, so now N3 is 5. Okay, so now we can somehow see the rule, right? So if you think carefully, you can find that here NT should equals to NT minus 1 plus NT minus 2, right? For example, N3 equals to 2 plus 3, right? So, okay, very good. And so this is basically the conditions, right? And from here, you can see that. So this relation is actually a famous relation, right? You can see this is nothing but the Fibonacci sequence, right? Okay. Or, you know, you can also understand this as a difference equation, right? There's a certain rule to solve difference equation, but so we're now going to the details of how to solving this. So you can see, Google it and check it online. Very easy to find. So basically, by solving this differential equation, we can find NT is nothing but this general form, okay? 1 plus 4 to 5, t plus 2. So we need to change it a little bit, right? Because the Fibonacci sequence starts from 1, right? It's 1, 1, 2, 3, right? But here we start from 2, so we need to shift it to the left by 2 units. So we have t plus 2, okay? So this is a very well-known result, right? This is a well-known result. Okay, great. So now we have the general form for NT. The next is to compute the limit, right? So let's compute it. So this equals to the limit 1 over t and the log NT, right? Okay, so let's plug NT in here. So we get this. T plus 2 minus t plus 2. Okay, so now let's compute the limit. Okay, so we can see that for this guy, so it's a log inside is a product, right? So we can basically separate them to get the follows, right? So we have 1 over t log 1 over square root of 5 plus 1 over t and this. Okay, very good. And now clearly this guy will goes to 0, right? And if we separate this guy, you can see that because we have 1 over t outside, right? And this inside is smaller than 1, so this guy also goes to 0, right? Therefore, the left term is, okay, so there's no this, right? It's nothing but 1 over t times 1. There should be a log, right? Yeah, log, okay. Okay, 1 over t log 1 plus root of 5 or 2t plus 2, right? That equals to t plus 2 over t log 1 plus root of 5 over 2, right? And when t goes infinity, this guy will become 1. So we just have a constant left, which is given by this guy, right? And if we compute it, that equals to 0.694 bits. So basically equals to the maximum value of HP in part C. Okay. So okay, and here on the hint, so they also have a question that why H0 is an upper bound on the entropy rate of the Markov chain. Compare H0 with the maximum entropy found in part D. Now you can see that the maximum entropy found in part D is they're the same with H0, right? But now the question is that why H0 is upper bound. This actually 1 over this. So this basically means that the number of allowable state, right? So basically 1 over n can be understood as a PMF for the uniform distribution, right? Therefore, you can see it's a log, therefore, all of state can be understood as a uniform distribution, therefore that is upper bound, right? Okay, so maybe let's repeat it here. So the reason H naught equals to this guy is an upper bound is because 1 over nt can be understood as a PMF of uniform distribution, which maximizes the entropy, right? Okay, very good. All right, so so I didn't. Okay, so this is basically what I wrote here. Okay, so just give a minute to take a look. The reason H0 is upper bound is because 1 over nt can be understood as a PMF of uniform distribution which maximizes the entropy, right? Okay, great. So now let's see our next question. Our next question is 4.9, so initial conditions. We need to show a Markov chain that, so this inequality is satisfied. Thus, initial condition x0 becomes more difficult to recover as future x unfold, right? Okay. Let's see. Okay, so now let's think about how can we solve this problem, right? So this basically means that, as further as the state went, right? So we can, so basically we have, by observing that state, so it will have more and more uncertainty for the initial state, right? So this is kind of similar with data processing inequality, right? So let's think about it. So basically we have x0 till x1 till xn minus 1 and xn, right? So from the data processing inequality, what we know is that the mutual information between x0 and xn minus 1 should be bigger than or equal to the mutual information between x0 and xn, right? So this basically means almost the same thing as what we show as what we want to prove here, right? Okay, so now, so this is data processing. Inequality, right? So here, basically, we can expand entropy, the mutual information in terms of entropy and get the following: x0 minus x0 given xn minus 1 bigger than or equal to entropy of x0 minus, right? Okay, and here we can cancel and h x0 on both sides. Therefore, we can get h xn x0 given xn bigger than or equal to this guy, right? So basically, it means that so this guy will increases with them. Okay, so we're done with the problem. Okay, very good. All right, so let's see our next question. So our next question is 4.11. This question, so we know that the sequence of x is a stationary process, but may not be a Markov chain, right? So now we want to determine which of the following inequality are true or not, right? So let's get started. Let's see the first one, this one, right? Okay. 4.11a. Okay, so the first one is that we want to prove a equality of this guy and this one, right? So because because x is stationary, right? Intuitively, I think they may be true, right? Let's try to see whether it can be true or not, right? Okay, so when you see a conditional entropy, right, basically you want to represent it in terms of another set of entropy or some form of neutral information, right? Okay, so let's try this. We can write it as joint entropy minus entropy of x naught, right? So now the next step is that because it's stationary, right, we can shift this guy, right, minus n on both states. They'll stay the same, right? So I have x0 and x negative n, right? Okay, therefore this will be equal to that, right? You can see that it's true, okay, for the first one. Okay, so now let's see the second one. For our second one is this is larger than or equal to that, right? So let's see whether it's true or not. So what we would like to see is that this guy, let's see, is bigger than or equal to okay. The idea of this problem is that, so let's see whether there's a chance that this guy can be smaller than this guy, right? So the easiest case to make this guy as small as possible is how about we make xn equals to x naught, right? And then how about we make xn n minus 1 and x naught independent, right? So by doing this, we can see we can still make a stationary Markov chain, right? So so given that, and we can see in this case, so this guy will be 0, which would be less than, or less than this guy, equals to x minus 1, right? As long as this is not 0, right? Okay, so this means that the second problem, it may not be true, okay? Okay, and also, so then, okay, let me see. Okay, and here, know that the only thing we can guarantee is that the sequence of x's are a stationary process, right? It may not be Markov, right? So this is clearly not Markov, but we can make this stationary, right? Okay, very good. Let's see the next one. Okay, next one is this is increasing in n, right? So basically, the way to deal with this kind of question is that we just need to increase n and see whether the value is increased or not, right? Okay, so let's try to see whether it's true or not. So we have this conditional entropy, right? So what we want is that we want to see whether this guy is bigger than xn plus 1 and so on or not, right? So basically, because xn is stationary, then we can move n up a little bit, right, till xn plus 2, right? And here we can see that, so this is not, we add n plus 1, for this guy, right? For this guy, we miss a component of x1 here, right? So basically, we need to add this x1 back. By adding this, we know conditioning will reduce entropy. Therefore, so it's bigger than or equal to xn plus 1 given x1, 2 until xn plus 2, right? Therefore, that is true. Okay. Now let's see part D. Part D is something similar, right? So I want to see whether this is a non-increasing in n, right? Whether it's a decreasing function of n. Okay, so we do the same thing here and see what we can get. hxn given xn till xn minus 1 and xn plus 1 till x2n. Also, we need to add an n here and see what happens. x2 till xn plus 2 till x2n plus 1. Right, again, now compared to here, increase the n, so we miss a x1, so we can add this back. Then we can see that we're done, right? So this indeed decreasing, because if we increasing n by 1, so we get this, right? Okay, that's true. All right, so now let's take a look at the next question, which is 4.33. So feel free to look at other questions, right? So they're all pretty good. Okay, for this 3, we have Markov chain x1 to x4. I want to show this inequality, right? So the mutual information between x1, x3 plus x2, x4 is less than this, right? So this may not be very obvious, right? Because from the data processing inequality, we know that this mutual information x13 is bigger than x14, but this 24 is less than 23, right? One is bigger, the other one is less, right? But overall, so what would be the relationship, right? Okay, so let's try to prove it. So this is 4 point, maybe let's use another page, 4.33. Okay, so our goal is to show this. Our goal is to show this inequality, mutual information between x13 and x2, x4 less than x1, x4 plus x2, x3. Okay, so no, there may not be a very obvious way to derive it, right? One way we just start from here, and hopefully we can get here, right? But usually, because they're pretty symmetric on both sides, right? The best way to do this is to just assume it's true and then we derive it, but every time we have an equivalent sign here, right? So make sure we can go back, okay? So that's how we do this. So basically, if this is true, then equivalently, we just need to show the expansion of this, right? Just write down this in terms of entropy, right? And x2. So when we do this expansion, so we need to make sure that we could cancel terms as much as possible, right? Therefore, it means that for the first one, we focus on x1 and x2. The second one, on the right-hand side, we also do this, right? x1 given x4 plus hx2 minus hx2 given hx3, right? Given this, so we can see our life may not be a lot easier, right? So we can cancel this and cancel this, okay? And after doing so, what we get also equivalently, right? So we can go back. So this is negative this minus this. Okay, great. And so maybe we can rearrange a little bit here, okay? So we want x1 given, we move x1 given x4 to the left hand side, minus hx1 given x3 less than or equal to minus, okay, so we're almost done, right? Okay, the next thing is that, so still we can now see which one is bigger, right? But how about combine these two and combine these two, right? Is there a way to combine? Okay, so the troublemaker here is that here x1, here is x1, they're the same, right? But the troublemaker is that here is x4, but here is x3, right? That is the troublemaker, okay? But remember that. So what we are working with now is a Markov chain, right? So for a Markov chain, so if we add a condition here, where we should add this one, right? Then we can combine these two, right? So what is the relationship between this and that? Right, so x4 is further away, right? Therefore, it doesn't matter. Okay, so this guy will be equal actually, right? Similarly, we can also add a term here. Also, what we should add is nothing but x4, right? Because we have x4 here, right? So now we're really familiar with that, right? So for this term, both of them have x4. So we have x4 here and x4 here. Then it will be a mutual information, right? So that will be the mutual information between x1 and x3 given x4. It's conditional mutual information. And on the right-hand side is the conditional mutual information between x2 and x3 given x4. Okay, therefore x4 doesn't matter, right? So it's both of them are given. And now, it's mutual information. Now, can we see which one is bigger? So clearly this one is bigger, right? What's that? So the reason is because of the data processing inequality. Okay, so let's say this is due to the data processing inequality, and then we're finished the proof, right? So when we write the proof, we just need to start from here, and then we can go back up to the top, right? Okay. Okay, very good. And now let's see our next question. So we're done with our chapter 4. So the next question would be our chapter 5. Okay, so let's try to find it. Okay, so the first question is 5.1. Okay, so in this question, so it's about uniquely decodable code and the prefix code, right? So we have a quantity here, which is the expected value of the 100th power of the code word length associated with the encoding of random variable x. Okay, so now we have two quantities, right? One is L1, the other one is L2, where L1 is the minimum of L over all the prefix or instantaneous code, but L2 is the minimum over all the uniquely decodable code. Okay, so now it asks you to see what is the relationship between L1 and L2. Basically, we need to answer which one is bigger. Okay? Okay, great. So which one is bigger? So in class, we talked about, so first of all, so let's try to recall, right? So the uniquely, we know an index code is uniquely decodable. I mean, the prefix code is uniquely decodable, but vice versa may not be true, right? So uniquely decodable is here, uniquely decodable. Okay, but prefix or instantaneous code is here. Okay, so prefix implies uniquely decodable. Okay, therefore, what does that mean? Let's see. The maybe let's write instantaneous codes are uniquely decodable, right? So this means that the space of, or the set of the uniquely decodable code is more than the previous code, right? If we minimize it over all the uniquely decodable code, right, it means that L2 should be less than or equal to L1. That's true, right? Because we have more operation space, right? And action space. So the space of uniquely decodable is bigger. Okay, great. So on the other hand, so we also learned about the Kraft inequality, right? So we know that since uniquely decodable codes satisfy the Kraft inequality. Okay, so they satisfy Kraft inequality. Meanwhile, we also showed that before that any code word length satisfying the crafting equality we can actually construct an instantaneous code, right? So for any length that satisfying the crafting equality, so we can construct instantaneous code. Okay? So what does it mean? So it means that if it's uniquely decodable, then according to that, we have a crafting equality, right? Given any length satisfying the crafting equality, then we can find a instantaneous code. Okay? So this means that so there might be some other instantaneous code that we can do better, right? Because for for any uniquely decodable code, and then we can find the corresponding instantaneous code that have the same length basically, right, for each L, right? Therefore, this basically implies that L1 is less than or equal to L2, right? Because for any uniquely decodable code, there's a corresponding prefix code, okay? Therefore, because of this and that, right, we can conclude L1 and L2 are equal, okay? Because L2 is less than or equal to L1, and L1 is less than or equal to L2. The only possible point is that they're equal. All right, so this is the 5.1. So now let's see 5.4. So this is to exercise the Huffman code, right? Okay, so the first part is to find the binary Huffman code for X, and then want to find the expected code length for this encoding, and then we need to find the ternary Huffman code. Okay, so let's try to do that. See, here is maybe this new page. This is 5.4. Okay, so let's see. We have seven symbols: x1, 04.9, x2, and let's just copy all of them here. X6 and X7. Okay, great. So now let's start the Huffman coding procedure, right? So it's binary, right? So every time we just combine two of them. So here we just pick the smallest two, then combine them, right? 0 here, 1 here. So here we get 0.05, right? And now we're gonna move up the ranking, right? Because the new symbol becomes bigger. So now we can move it to here. So now here is 0.05, and we have all the rest here, and right, okay. So next one would be we combine these two together, right? Okay, so let's do that. So here is 0, here's 1, 0.08. Okay, so now we need to move this up to here, right? And then also to remember that here is 0.05, right? So we move up to here. Okay. Okay, so the next step is to combine these two, right? 0, 1. And now we have 0.13, right? And then we move up to here, and then this guy will become lower, right? Next is to combine these two, right? This is 0.25, and we have 0 here and 1 here. All right. Okay. Next one is to combine these two. We have 0.51, right? And then we have 0, 1 here. And next, we're gonna move this up and then get this here, 0, 1, and then we're done. Okay. So next, let's see the code word, right? Let's see the first one. The first one is that only have a 1 on this path, right? So we have a 1 here. And let's see for the second one, we have a 0 and 0, right? Second one have 2 zeros. And let's see the third one, x3. x3 we have nothing, 1, 1, and 0. Therefore, it should be 0, 1, 1, right? So we write it from the left to the from the right to the left, right? And the x4 is 0, 0, 0, 1, and 0, right? There should be 0, 1, 0, 0, 1. Okay, here should be 0, right? And similarly, you can get all of them, right? So 5 is 0, 1, 0, 0, 1, and 6 is 0, 1, 0, 1, 0, and last one is 0, 1, 0, 1, 1. Okay, great. And next step is so this is for part A, right? And next is to compute the average length. So that is nothing but Li times Pi, right? That equals to first one 0.49. So the length of that is 1, right? Plus 0.26 times 2 plus 0.12 times 3 plus 0.04. Yeah, all of them are like the length of 4, right? So we can add them all together. 0.03, 0.02 times 4. Okay, so if we compute it, we're gonna get 0.02. Good. Okay, very good. And the next one for part C is to get a ternary code, right? Okay, let's see. Let's write everything down here. I still have x1, x2, 3, x4, 5, 6, and x7, right? And here the probability is same as before. Okay, so we're gonna see later that we do not need any dummy variable here, so we just do the combination. Okay, so then we need to pick a symbol here, right? Doesn't matter. It could be ABC, it could be 0, 1, 2, right? We'll just pick 0, 1, 2 here. So the procedure will be identical as before. So here is 0.09, and then this will move up here, and then this will be here. Okay, the next step is that we're gonna combine this 3, 0, 1, 2. Okay, and here we get 0.25. And lastly, we just combine this 3, right? And we have 0, 1, 2 here. Okay, so now we can write it down. This first one is 0, second one is 1, third one is 2, 0, 2, 1, and 2, 2, 0, 2, 2, 1, and 2, 2, 2. Okay, and that will be the answer of this question. Okay, let's see the next one. Next one is 5.6, bad code, right? So I ask you to see which of the code cannot be a Huffman code, right, with this probability assignment. Okay, so let's see the first one, 5.6a. So the way of thinking this problem is that, so we know Huffman codes are optimal, right? If you see this code may not be optimal, then we know it may not be Huffman code, right? Okay, clearly for this guy, it could be a Huffman code. Like we have the probability like half, 1/4, 1/4, and then we could construct Huffman code. Let's try this. Okay, for the second one, B, so the code word are 0, 0, 0, 1, 1, 0, and 1, 1, 0, right? And from here, clearly this is a prefix code because none of the code word is the prefix of other codes, right? And the other thing is that, so we can observe that this 0 is not needed, right? If without this, so the code will still be a valid code, but with a better performance, right? Therefore, this code is not optimal, right? Right, we can make an optimal code by like this, a better code like this, right? Therefore, it is not a Huffman. So we should say cannot be Huffman code, right? Okay, for part C, so it's very similar. We have 0, 1, 1, 0. So I have only two symbols here, right? For two symbols, clearly this is not optimal, right? We can make something like 0 and 1. That'll be enough, right? And we say 1 bit. Like clearly this is not optimal. Okay, so it means that cannot be Huffman codes, right? Next, let's take a look at the next problem. Our next problem is problem 5.8. So in this problem, we consider a Markov chain. So here is a transition probability, and we have three states in the state space, right? And okay, and here, so the problem asks us to design a code, right, in the following procedure, right? So the first is that note the present symbol xn is I, and then select code ci for the next one, right? And then the next symbol would be uh, select another code for the next symbol and so on, right? So this is basically the procedure of the design, okay? And then after designing the code, so we need to see what is the average message length of the next symbol conditioned on the previous symbol xn. So this is the conditioned average code length, right? And then we need to compute what is the unconditional average number of bits per source symbol, and then we need to relate this to the entropy rate of the Markov chain, right? It means that we need to compute the entropy rate, right? Okay, so let's get started for this problem. 5.8. So now let's recall. Let's recall the transition probability, right? So I have un. Here is un minus one, and we have three states: S1, S2, and S3. Here S1, S2, and S3. So the probability is like this. Okay, and then 0, half, half, right? So the design of the code could be as like a given state, right? And then how can we design the state of the next, I mean the code of the next state, right? So it means that we should have three code here, right? So the first code is given by this line, right? If the previous state is S1, then the next state is we have probability half to be S1, probability 1/4 to be S2, and the probability a quarter to be S3, right? We can, use a Huffman code for this, right? So if you do that, let's make it shorter. So if you do that, you can see that we can basically give half a 0, right? And 1/4, let's say a 1, 0, and the third one, S3 is 1, 1, and that is basically the code. We call this SC1. And similarly, we can design the code for S2, right? So S2 could be identical at 0, 1, 0, 0, and 1, 1, and C2, and last one. So that would be pretty straightforward, right? So the first symbol, the probability is 0, then we don't need a code here, right? And then we can have a 0 and a 1 here, and that is C3. Right, so this is basically for each given previous symbol, so we can use a Huffman code for the next one. Okay, so now let's compute the average code length. So let's say ln given as 1 as the last state, right? And then we have half multiplied 1 plus a quarter multiplied 2 plus a quarter multiplied 2, that is 1.5 bits, right? For ln as 2, so that will be something very similar, right? This plus so that'll be the same. Okay, so for the last one, it'll be like this, half times 1 plus half times 1, that'll be 1 bit, right? All right, great. Okay, so now we want to compute, this is a conditional average length, right? So now when you want to compute the unconditional average length, in order to compute that, we need to compute the stationary distribution of the Markov chain, right? Where, again, we need to use this, multiply the transition probability, which is half, 1/4, 1/4, 1/4, half, 1/4, 0, half, half, right? And remember that the probability of the three states add up together will be give you 1, okay? And then solving these equations, we could obtain that pi equals to 2 over 9, 4 over 9, and 3 over 9, so that is 1 over 3, okay? And given that, we could compute the average length as follows, right? So that is 2 over 9 times the first symbol, right? For the first symbol, I mean the first code book, right? So the first code is basically this one, right? So we have multiply 1.5 plus 4 over 9 multiply 1.5, and then 1 over 3, then multiply 1, and that will give us what? 4 over 3. Okay, that is the average code length in total. And next, we're going to compute the entropy rate of U, right? That is nothing but hx2 given x1 because it's stationary and it's a Markov chain. Okay, and then this equals to the follows, right? Pi I given x2 given x2 given x1 equals to I, right? Okay, great. So this is the definition, and so now we know everything, right? So we know all the pi's, and we know this conditional entropy because we know the conditional probability distribution function, right? Therefore, so we can compute this also as 4 over 3 bits. Therefore, we can, so we solve the problem, right? So we can see that basically this equals to our Ln, and so therefore we could conclude that by using this approach, this coding approach, so the maximum compression is achieved, right? So, okay, which is stated here, right? So this maximum compression can be achieved, right? So let's see the next question, so which is question 5.12. So in this question, we're going to compare the Shannon codes and the Huffman codes, right? And consider random variable x that has 4 values, and here is the PMF. So the first part asks us to construct a Huffman code, okay? And then in the second part, we show that there exists 2 different set of optimal lengths for the code words, namely show that code word length assignment 1, 2, 3, 3 and 2, 2, 2, 2 are both optimal, okay? So basically this means that we have 2 ways of construct Huffman code, right? And both of them have the same average length, right? So let's try to construct the Huffman code in 2 ways. Okay, so we're gonna solve the A and B together. So here's A and B, right? We just construct the Huffman code in 2 ways. And here is, let's say x1, 1/3, x2, 1/3, x3, you have 1/4, and x4, we have 1 over 12. Okay, and as our rule, right, so we're gonna combine, so these 2 together, okay, and have 1/3 here, and we'll have 0 and 1, okay? And then next, so we're gonna, 1/3 should be, so according to our rule, right? So 1/3, we just go make it the highest, right? And then we have the following symbols, right? And now all of them is 1/3, right? We'll just combine these 2, right? We have 0 and 1. Okay, here's 2/3, then we'll make it the top, and that will be the bottom, okay? And then we can combine this, put 0 and 1 here, right? By doing that, we can see that for x1 we have a 0 and a 0, so 0, 0 for x1. And similarly, you can see x2 will be 0, 1, x3 is 1, 0, and x4 is 1, 1. Okay, and then we can see, so this code word length is the 2, 2, 2, 2 case, right? Because we have a special rule for the construction, but so we don't need to follow our rule, right? So we can do something else. So let's see, let's do this, write all of the symbol again. Okay, and as usual, so we need to follow the rule of the Huffman code, right? So we have 1/3. Okay, so now if we do not move this 1/3 to the top, then we can make some code longer, right? So let's basically do something like that. Okay, combine these two, have 0 and 1, for example, and then we have 2/3. Okay, so now we can follow our rule. So to have a 0, 1 here, and then combine these two. Okay, and here we can see the first one will give you a 1, and here is 0, 0, here is 0, 1, 0, and 0, 1, 1. Okay, and this is a case where we have the code word lengths are 1, 2, 3, and 3, right? So we can see both of them would be possible, and if you verify that, both of them will have the same code word lengths, right? That is a part A and part B, and for part C, conclude that there are optimal codes with code word lengths for some symbols that exceed the Shannon code length, right? So if you remember, as we said, for the Shannon code, right? So although there may be some code word that's very large, but the probability of that will be small, right? So here, what we would like to see is that although Huffman code is better than the Shannon code in general on the average length, but there may exist some code word where the Shannon code might be better. Okay, so let's see. So let's construct the table of the code word lengths. Let's see x1, x2, x3, x4, and then now we're gonna compute the length, right, for the Shannon code. So this would be the length. Okay, so px is given by 1/3, 1/3, 1/4, and 1/12, right? Here we can see that first one should be 2, 2, 2, that's why it's 4, right? Because it's 1 over 12. And on the second row, let's write the Huffman code, right? Right, maybe let's pick this guy. So we have 1, 2, 3, and 3, right? So in this case, we can see that so for the first, second, fourth symbol, the Shannon code are worse or equal, right? But for this symbol, the third symbol, right, for this guy, and we can see that here the Shannon code is better, right? Okay, so this is a interesting observation. Okay, so again, Huffman code is the best in terms of the average length, but for the individual code word, it may not be the shortest. Okay, great. So next, let's consider the next problem, which is again Huffman codes, 5.16. So in this case, we have 1, 2, 3, 4, 5, 6 symbols, and here is the PMF. So the first question asks us to construct a binary Huffman code for this random variable, and what is the average length, right? Okay, so we have done this so many times, right? So let's do this again. Okay, so let's do this again. Here is 516. So now let's write down all the symbols here. We have A, B, C, D, E, F, and the probability is 0.5, 0.25, 0.1, 0.05, 0.05, 0.05. Okay, for the binary Huffman code, we'll just do the usual stuff, right? 0, 1, here 0.1, okay, and then we can shift it up to here and keep everything else as the same location. Okay. And then next we're gonna combine what? These two, right? So now here we have 0.15. Okay. Then we can shift it to here. So this is 0.1. Okay. And keep everything the same. So next is here. So this is 0.15. This is 0.1. Put a 0, 1 here, and then this is 0.25. Okay, and then we can do this. Okay, and 0, 1. So this is 0.5. Okay, and lastly, we can make it equal to 1. Okay, and then we're done, right? Now let's see again. You can work it out on your own, right? But obviously, so the first one would be a 1, and then second one 0, 1, and then we'll have 0, 0, 0, and 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. Okay, again, it may not be the only choice for the Huffman code, right? There might be some other solutions. Okay, so now let's compute the average of the code word length. That is 0.5 times 1 plus 0.25 times 2. And for the rest of the code word, it all has 4 binary symbols, right? We just combine them together. 0.1 plus 0.05 plus 0.05 plus 0.05 and then times 4. That'll give you 2 bits. Okay, very good. So this is basically the first part. And that's the second part. Second part is to ask you to construct a quaternary Huffman code. Okay, and we use symbols A, B, C, and D. What is the average length of this quaternary Huffman code? Okay, so the procedure will be the same as before, but now we want to see whether we need any dummy code or not, right? So in this case, indeed we do. So remember the procedure, so we need to have a k, right, where k denotes the number of merges, right? K should be bigger than or equal to n minus 1 and d minus 1, where n is the number of symbols. Here we have 6, and d is the size of the alphabet of the output, right? Now we have A, B, C, and D with 4, okay, and then this is 5/3. So we can see, remember that k is the number of merges, so k has to be integer, so k is 2, right? Because k has to be larger than or equal to 5/3. Okay, next we need to compute the number of dummy symbols. Okay, so that equals to 1 plus k d minus 1 minus n, right? So if you don't recall this, just look at your lecture notes. Okay, and then we plug all the numbers in. 1 plus 2, 4 minus 3 minus 6, that is 1 plus 6 minus 6 equals 1, right? This means that we need to add 1 dummy symbols. Okay, so now let's get started. A, B, C, D, E, F, and G, right? Where G is the dummy symbols with probably 0. Okay, then just copy and paste all the probability here. Okay, so it's a quaternary, right? So it means that every time we combine the 4 symbols with the lowest probability, okay, we just combine these 4. Okay, and here we have A, B, C, and D. You just put them randomly, doesn't matter, but we just do this. And now here is 0.15. Okay, so we can make it bigger, larger here. Okay, and then we just have one more step left here, right? So which is this. A, B, C, and D, and then we're done. Okay, so now let's write down code word here. So the first one, A, so we have a small a here, and B is a small b here, and C is small d, and from D to G is CA, CB, CC, and CD. Okay, and clearly, so CD doesn't matter, right? Because G is not a real variable, a real symbol. Okay, so ln equals to nothing but. So we can see the first 3 have length 1, right? 0.5 plus 0.25 plus 0.1 times 1. add 0.05, add 0.05, add another 0.05, then 1 times 2. Okay, so this is equals to 1.15. So this, the unit of that is not bit anymore, right? It's called quaternary symbols. Okay, very good. So that is for our part B. Okay, let's see what should we do for part C. Part C is kind of interesting, right? So they give us a way to find a binary code. Okay, the way we do that is that we use a quaternary code first, and then translate each symbol to 2 bits, like that, right? And now we need to compute what is the average length of the binary code for the random variable above constructed by this process, right? Okay, so let's try to do this. Okay, so now we can see that the only difference here, okay, yeah, the only difference here is that, so now this is 1 quaternary symbol, but it's 2 binary symbols, right? So the computation is rather straightforward. So we just have the same thing before, right? But instead of multiply 1 here, we multiply 2, and then we do the same thing. Multiply 4, right? Before I multiply 2 here, right? Okay, and then let's see, this give us 2.3 bits. Okay, so you can see this is how well we're doing if we use the this procedure to generate the binary code, right? Okay, so let's see the next one. The next one is that so this LH denotes the average length of the binary Huffman code, and this LQB is the average code length constructed by first building a quaternary Huffman code and then converted into binary code, right? Then we need to show this inequality, right? You can see by doing this, so we're not extremely far away from the performance of the binary code or the optimal performance, right? Okay, so let's see how we can do this. That is our part D. Okay, so first of all, yeah, let's first write our goal here, right? So that is LH less than or equal to LQB less than or equal to LH plus 2, right? Okay, so is this direction familiar, right? Right, we know that the binary Huffman code is optimal, right? Therefore, for this LQB, that is from another construction, right? It has to be bigger than or equal to LH, since LH is optimal already for the binary codes. Okay, so now we need to prove the other direction holds, right? We need to prove this is less than LH plus L2. Okay, let's see whether that is straightforward or not. So we introduce a notation of LQ, so that is to denote the optimal quaternary code. Okay, and so here we know it's a prefix code, right? For a prefix code, we can actually show this bound. Right, so here this 4 basically means that the base of the log is 4, okay, instead of 2. Here we can observe that the relation between LQ and LQB is LQ equals to LQB over 2, right? Because every quaternary symbols will be translated into 2 binary symbols, right? And similarly, we can also get that the relation between this guy and the binary case is also this equals to the binary entropy over 2, right? Because the base is 4 and 2, right? So that is straightforward to see. And lastly, here we also have this plus 1, okay? And now we multiply 2 on both sides, I mean on all of them. So we could get H2x less than equal to LQB less than equal to H2x plus 2. Okay, so this is what we can get. So now we need to introduce the LH, right? So now we know where the LQB will sit, right? So let's see. So then from here we can see that we know the LH is bigger than or equal to the entropy, right? And we know the LH is less than or equal to LQB, right? Because of here, right? Okay, and then LQB is less than or equal to H2x plus 2. Okay, and again, we use the relation of this again, right? LH is larger than H2x, so this is less than LH plus 2. Okay, from here, we can basically see that LH is less than or equal to LQB, less than or equal to LH plus 2. Okay, and this is what we want to show. Right. Next, let's see part E. In part E, it says that the lower bound of in the example is tight, right? So it means that these two can actually be equal. Give an example where the code constructed by converting an optimal quaternary code is also optimal binary code, right? So then you may think what that would be the case, right? So when this procedure in C is optimal, right? We do not lose anything, right? Actually, the case where it's optimal, that is the uniform case, right? So if let's say we have 4 symbols, A, B, C, and D, and each of them have the same probability distribution, okay? And then if you do the Huffman procedure, you'll get this, right? And then, right? So this is a way that you construct the binary code, right? Okay, so I have 0, 1 here. Okay, and then we're done, right? So now you can see the code word will be 0, 0, 0, 1, 1, 0, and 1, 1, right? And you can see here LH is basically 2 bits. Okay, so now let's see the case of the quaternary, right? So that's A, B, C, D again, 0.25, right? So this is very straightforward. We just have 4 symbols here, so we just combine them all at once. Okay, we have A, B, C, D here, right? And then we're done. So the code will be A, B, C, and D. And for each one, we just translate it into 2 symbols. Let's say 0, 0, 0, 1, 1, 0, and 1, 1, right? And then you can see LQB will be nothing but 2 bits, right? Then they are the same, okay? So this procedure can be optimal in some cases. Okay, great. So, and now let's see the part F. So the upper bound, this is not tight. In fact, a better code is this is less than LH plus 1 will hold, right? And prove this bound, provide an example where this bound is tight. Okay, so let's see how we can solve for that. So this is part F. So notice that here, what we would like to show is LQB equals to LH plus 1, right? So in this case, so basically the idea is that when we want something about the LH to be something odd, and then if we append 1 bit in the end, then that would be represented by some quaternary symbols, right? So if we reverse the procedure, then we could have exactly this relationship, right? So maybe, for example, let's say if you have 8 symbols, let's say from x0, x1, x2, x3, x4, x5, x6, and x7, right? So in this case, maybe let's assume they all with the equal probability, but the probability all of them is 1/8, right? Okay. So in this case, let's assume we can do the Huffman procedure, but we should be able to get something like 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1 0 0 1 0 1 1 0 1 and 1 0 1, let's see, so 1 1 0 and 1 1 1, right? So those are a possible configuration of the Huffman codes, right? And in this case, so what we would like to do is that all of them are odd, right? So we would like to append a bit in the end, right? It could be 0 or 1. For example, let's do 0. If we do this, okay, we append a 0 everywhere, okay? And in this case, so basically we have each of them have 4 symbols, right? So now let's say we can use this mapping, right, reversely to get our quaternary code, right? For example, so this guy will give us what, AA, and over here will give us A10 AC, and this is BA, so this is 01 is B10 BC, right? And also this one would be 10 is CA, and this guy is CC, right? And this guy is DA, and here we have D10 is C, DC. Okay, so that is we can double check. So this should be a valid quaternary code, right? It's a prefix free, right? So it's prefix. Okay, so basically that would be the idea, right? So if we construct a quaternary code for these A symbols, we're gonna get something like that, right? And then using this mapping, so we can map each of them into the binary bits, right? Then we can double check the relationship between the relationship of this would hold, right? Because we have exactly 1 bit more, right? So that is basically the procedure, okay? And this is our example, okay? So maybe let's write it down here. So what we would like to do is as follows. So we let append at most, right? In general, so it may not, so maybe some of the lengths of the code words would be odd, right? It may not be all of them are odd. So we append at most 1 bit, right? Such that they're all even, right? At most 1 bit, but they could be 0 or 1, doesn't matter, okay? To the binary Huffman code to make the lengths of each code word an even number, okay? And then we can see this new code is still prefix code, right? Okay, and then we can use the inverse process of C to have a quaternary code as we just described in the example, right? Okay, great. Next, let's take a look at the next question. Okay, so our next question is question number 4, optimal codes for uniform distributions. So in this question, we consider a random variable with m equal probable outcomes. The entropy of this information source is obviously log 2m bits. Describe the optimal instantaneous binary codes for the source and compute the average length lm. The second part is that for what value m, that's the average code word length lm equals to the entropy, and then in part C we know that L is less than h plus 1 for any probability distribution, redundancy of a variable length code is defined to be rho equals to L minus H for what values of M is the redundancy of the code maximized. What is the limit value of this worst case redundancy as M goes to infinity? Okay, so let's see the first part of that. Okay, so this part is that, so we know the probability distribution is uniform, then describe the optimal prefix binary code, okay, and compute the average code word length. Let's see how could we consider this problem, okay? So, so because it's a uniform distribution, right? So if we construct a Huffman code, so actually what we can prove is that, so we can see that two code word lengths differ at most one, right? Cannot be two, right? So use a similar idea that we provided in class, right? Just use prove it by contradiction. So it's not that hard to show that, right? So basically, this is somehow intuitive as well, right? So if we construct a code tree, right, it'll be something like that. Okay, and because it's all uniform distribution, right, we at most have one more layer, something like that. Okay, and then so it depends on m, right? So whether it's integer power of 2 or right, then we can see there the code might be have this length or this length, right? The difference is at most 2, right? So if we call second, I mean this is layer 1, that's layer 2, right? Then so what we can see here is that, so this would be our layer log 2m floor, and the last one would be log 2m floor plus 1, or we can write it as the saving of this. Okay, and actually given this, we could compute the number of nodes in this layer, right? So we know the number of nodes in this layer, right? It's 2 to the power of this number, right? We can compute the number of nodes this layer, so which is nothing but m minus 2 to the power of this guy, and then multiply 2, okay, right? So basically, if we use this minus that, right, so we can, how to explain that? So basically, so for each node here, there's a corresponding node here, right? So basically, this minus that is the total number of these guys here, right? We need to multiply 2 to get the total number of nodes here, okay? And so this is basically the property of the optimal code that we need to describe, right? And then the next step is to compute the average code word length, right? So we know this is PMF, and then we just need to times the length of the code word, right? And okay, so let's see. So the total number of the code have this length is this number, right? And then we use m minus that will be the total number of will be the total number of code word with length of this, right? So this is basically what we are going to write now, and let's give a notation for this guy, right? Let's denote this guy as t, right? The overall number of nodes in this layer is 2 times t, right? So that can simplify our notation. So here we have 2t multiply the sale of this guy and plus m minus 2t, and then the floor of this guy. Okay, and that's basically our average code word length. Okay, so now we can do some simplification here, right? So here we can see that So first of all, we can take this m minus this out, right? M minus floor of this guy. And then we can see 2t multiply this guy minus 2t multiply this guy, right? So that is to add 2t, and then we have this minus the floor, right? Okay, and clearly this is 1, right? Okay, and then we have 1 minus m this plus 2t, okay, and then that equals 2 plus 2t over m, right? So this is basically the average code word length. Okay, so now let's see our part B. Part B, what is the value of m? Does the average code word length Lm equals to the entropy H equals to that? Okay. Yeah, so the notation here they use Lm. Let's change it to Lm. So the meaning of this is slightly different compared to what we use in class, right? For part B, we need to, for what value of m does the average code word length Lm equal to the entropy log 2m, right? Then we can just observe it, right? So what we want is this guy equal to that, right? So that is not very hard to do, right? So basically, it basically means that we don't want this part, right? We want this to be the whole tree, right? Therefore, what we need is the m is to the power of something, right? Where k is an integer, okay? So in this case, we can double check. So t will be basically 0, right? So you can see the definition of t is like this, right? In this case, so that will becomes m and t will be 0, right? So this is basically part B. And now let's see part C. Okay, for part C, so we want to, so we define the redundancy as the difference between L and H, right? So now what we would like to do is to find values of m such that the redundancy of the code would be maximized, right? So basically what we want to do is that we want to maximize this, right? Okay, so and then we need to find the limiting value when m goes to infinity. All right. Okay, so let's see how we can do this. So basically, so in this problem, we want to so what we would like to do is this Lm minus the entropy, right? So here, so I mean this is assumed to be a log 2m, right? So therefore, we need to make this a little bit more approachable, right? So we don't want this floor here, okay? So the trick here we use to get rid of the floor is that. So we can see m can be equals to 2 to the power of k for some k, right, at t, okay? So then, given that, we can write rho equals to Lm minus h as this, log m floor plus 2t over m minus log 2m, okay? And because of this assumption here, right, we can see that the floor of this guy will be nothing but k, right? And then we add 2t over m and minus log m equals to 2 to the power of k plus t, okay? Now, in order to maximize that, so we know m is between 2 to the power of k and 2 to the power of k minus plus 1, right? So in order to maximize this guy, it is equivalent to find the optimal value t to maximize that, because all other values are fixed, right? Therefore, what we can do is that we do the derivative of rho with respect to t, and then solve for the best t, right? That is equivalent to solve for the best m. Okay, so now let's try to do the derivative of this. Okay, and what we can get is the following. So you can try this and see whether you get the same result with what I did here. To the power of k plus t times 2 minus 2t. It's just a derivative, right? And then here we have this guy, 1 over ln 2, okay? And if we let this guy equal to 0, then we could get t star equals to 2 to the power of k 2 ln 2 minus 1. So that is optimal t, okay? So the next step, so the next step is that we want to see what is the best row, right? And I believe that after finding now we have t star, then it means that we have the best m, right? And then we need to let m go to infinity such that to see the limiting value of this worst case redundancy, right? Okay, so what we should do next is that we're gonna compute the row and evaluate this row at, let's say, row star, evaluate the row star at t star, okay? So that is basically this guy plus t star minus ln 2 to the power of k plus t star over ln 2, okay? Okay, so now let's compute it. So what we do here is that we just plug in t star, which is 2 power of k 2 ln 2 minus 1, and upstairs is 2 times 2 ln 2k 2 minus 1 minus 2. Okay, here just some algebra, right? So we need to be careful here. Okay, and finish this. Okay, great. And now we can see that. So for this guy, right? So if we separate on the bottom, so what we can get is that basically we can take this 2 to the power of k out, and we can get k ln 2. Add left is a ln 2 ln 2, right? Because the minus 1 can be cancelled, right? And over ln 2, okay? And then we can see that this guy equals to k plus ln 2 over ln 2, okay? And also we can see this guy, so we can take 2 to the power of k and then cancel it, right? So then for the numerator, this is what we get, and in the denominator, this is what we get, okay? And you can see that this k and this k can be cancelled, right? Therefore, so that equals to 2 ln 2 minus 1, 2 ln 2, okay, and then minus ln 2. So we can separate this ln 2, right? Ln 2 plus ln 2 over ln 2, okay? Then we have 2 minus 1 over ln 2 minus 1 minus ln 2 over ln 2, okay? So that is 1 minus 1 over ln 2 minus ln 2 over ln 2, okay? All right, so yeah, my result is that it's not a function of k anymore, and so this means that when k goes to infinity, it'll still be like this value, okay? So yeah, this is what I computed, right? So if you have different answer, please let me know, right? Next, let's see the next question, which is question number 25. So in this question, optimal code word length. Okay, let's see. Although the code word length of an optimal variable length code are complicated function of the message probability P1 to Pm, it can be said that less probable symbols are encoded into longer code words. Suppose that the message probability are given in the decreasing order like that, right? So be careful here. So P1, P2, there's no equality sign here, right? That is kind of important. And then for the first one, we want to prove for any binary Huffman code if the most probable message symbol has probability P1 bigger than 2/5, then the symbol must be assigned a code word of length 1. And the second part is kind of similar, right? So if this most probable code word is less than 1/3, then the length of this symbol has to be at least 2. Okay, so let's try to prove that. Okay, this is 525. Okay, let's try to prove it for A. Okay, so now what we want to do is that we want to prove L1 is 1, right? So normally we prove it by contradiction. So we let L1 bigger than or equal to 2, okay? So then let's see what is a contradiction, right? So normally, as we introduced in class, so under this condition, basically what we may want to show is that we can find a better code, right? Then, since it's optimal code already, then we cannot find a better code. Then we show that is a contradiction, right? Okay, so let's see how we can prove that. So without loss of generality, so basically let's assume the code tree look like this. Okay, so we may have something like that. So this is the code tree for Huffman code, right? Okay. Yeah, maybe something like that. Okay, so let's mark the numbers here, 0, 1, 0, 1, 0, 1. Okay, so now without loss of generality, so we assume let this node to denote C1, and we know this P1 is bigger than 2/5, so that's the largest probability, right? Okay, so now we're going to introduce some new notation, so that is the idea of this proof. So basically what we're going to assume here is as follows. So how about we let's say we denote so this code word as C1, right? I mean, this is a bigger C1, right? This C1 means that it's for all the code start with 0, 0, right? So because it's on this branch, so that start with 0, 0. Okay, and we can see, so all this code, we call it C2, so that start with 0, 1. And for those code, so we call that C3, so that start with 1, 0, and here is C4, and that start with 1, 1. Okay, so yes, so that is basically all the code word. I mean, we can categorize all the possible code words into these 4 categories, right? So here, so what we know is that because P1 is bigger than 2/5, so we know the probability of C1. We say that's P1. That's bigger than 2/5, right? So because of that, we can see all the probabilities here, right? Let's say P2 plus P3 plus P4, right? So that will be less than 2/5. Okay, so if 3 of them is less than over 5, so it must exist 2 of them less than 2/5, right? Therefore, without loss of generality, so we assume that we let C3 plus, let's see, P3 plus P4, that is less than 2/5. Okay, so let P3 and P4 that is less than 2/5. Okay, So now let's see what we can do, right? Because these two code words together, right? Maybe let's write something like that. So all the possible code words here, so their probability is less than 2/5, right? But their code word length is bigger than the code word length here, right? So now what we're going to do is to exchange this and that, right? It means that we move this tree to here and move, from here to here. Okay, so by doing this, we can see that we increase the length of this code by 1, but they are with probability less than 2/5. And but if we move this guy to here, we shorten the length by 1, but the probability here is bigger than 2/5. Therefore, we reduce the code word length, right? So that will lead to a contradiction, right? So what we do is that we're gonna exchange C1 and C3, C4, therefore to get a better code, and then we have a contradiction. Okay, so this basically means that L has to be 1, right? So L1 is 1. It cannot be 2. Okay, so the reason that P1 has to be bigger than P2 is that there's only one largest probability here, right? We don't have any other largest probability in some other places, right? Okay, that is very important. Okay, great. So now let's see part B, right? So part B is very similar compared to part A, right? So in part B, what we want to show is that if P1 is less than over 3, then we want the code word length is bigger than 2, right? Again, we use proof by contradiction. So what we do here is that we let L1 is 1. Then again, we use a similar idea here. We build this tree like this, okay? So this is clearly our C1, right? And now for the rest of the code, okay, let's say we have two categories, right? So one category is, let's see, maybe I use a different color here. So let's call, maybe let's, here 0, 1, 0, 1, okay. So let's call all the codes that are here as C2 and all the codes that are here as C3. Right here, clearly C2 is the code starting with 1, 0, and C3 is the code starting with 1, 1. Right, in this case, we can show that the probability here, P2 plus P3, should be bigger than 2/3, right? Because P1 is less than 1/3. Okay? So this basically means that at least one of them has to be bigger than 2/3, right? Without of loss generality. Okay, so we assume that P3 is bigger than 1/3. Okay, so now we know this probability is bigger than 1/3, right? So now is there anything that we can do, right? Because this guy has a bigger probability, right? So what we can do is that we can make C1, let's say C1 to here, and make all of this subtree to here, right? Then we can again reduce the average code word length, right? So basically, we're gonna exchange this and that, okay? So this basically means that we exchange C1 and C3 to get better code, okay? Therefore, we'll have a contradiction. Therefore, L1 has to be bigger than or equal to 2. Okay, then we finish our proof. Okay. All right, so this is the proof of this one. So let's see our next question. So the next question is our question number 30. Okay, so relative entropy is the cause of miscoding, right? So yeah, this is relatively straightforward question, right? So in this question, so we have 5 symbols, and we have a true probability, and we have an estimated probability, and then we have a code word designed according to P, and a code word designed for Q, right? Okay, so the questions are as follows. So for the first one, we need to compute all the entropy and the relative entropy. Okay, so let's see how to compute that. So those are extremely straightforward, right? You just use the definition, right? Like HP equals to this guy. Okay, and then we just need to add all the numbers here, right? Plug all the numbers in, and then we can get. So I'll just write down the solution here, and you can double check whether see whether that's correct or not. And for HQ, so it is identical, right? The only difference is that now we have a probability of QX, right? Then that is 15. We can have 2 bits, okay? And for the third one, so it's the relative entropy between P and Q. That is this guy, right? Again, plug all the numbers in, we get 1/8 bits, and the relative entropy between Q and the P, again, is almost identical. We just replace position between P and Q, right? That'll give you what, 1/8 bits as well. Okay, so that's basically for part A. And for part B, the last 2 columns represent the code for the random variable. Verify that the average length of C1 under P is equals to entropy P. That C1 is optimal for P. Verify that C2 is optimal for Q. Okay, so let's verify that. Okay, so basically, let's say ln C1. So this notation means the length of C1. Okay, and then the distribution is according to Px, right? And then L1. So we just, again, here we just plug all the lengths in here, right? So 1, 2, 3, 4, 4. Okay, and then we can get, this is 15/8 bits equals to HP, therefore it's optimal, right? And then for the C2, what we do is that we want to compute this one, right? The only difference here is that we have L2 here and we have Q here, and then if we compute it, so obviously that equals to that is equal to HQ, right? And the next question is that now let's assume that we use code C2 when the distribution is P. So what is the average length of the cohorts? By how much does it exceed the entropy P, right? Okay, so let's verify that. Okay, so we denote this as L prime C2, right? So basically, we just use this probability and then L2. So we can see this is 2 bits, okay? And now if we want to see the cost, we use this number and subtract the entropy of P, right? That is 2 minus entropy of P is 15/8. So here basically what we get is 1/8 bits. Okay, and we can see this equals to the relative entropy of PQ, right? And then let's see the last part. So last part is the reverse, right? What is the loss if we use code 1, but when the distribution is Q, right? Okay, so basically for D, we denote this as L prime, L1, C1. So now the true distribution is this guy, and that, then this is 17/8 bits, right? So now we can compute the difference using the same way. Okay, then that'll give you what? 17 over 8 minus 2. That is again 1 over 8 bits. Okay, and this is basically the relative entropy between Q and P, right? Something like that. All right. Okay. So now let's see our last question. So which is question 39. Okay. So in this question, entropy of coded bits. Okay. So we have a code that is a non-singular code, but non-uniquely decodable, right? Okay. And we denote the entropy of X as this, and then we need to compare this guy and this guy. Okay. So let's do that. Okay, so we know the code for X is that. So this is non-singular. It means that we have one-to-one mapping, but it's not uniquely decodable, meaning that if we consider sequence of the code word, right there, so the mapping is not one-to-one. All right. For part A, okay, because the code is non-singular, right? So this basically means that we have one-to-one mapping, right? Therefore, if the code and the symbol has a one-to-one mapping, their entropy should be the same, right? Okay. On the other hand, for part B, so this is the code, okay? And right, so this is not singular, which means that it's a many to one mapping, right? It is possible that if we consider a sequence of the code word, right, it's not uniquely decodable, right? Therefore, we can see the possibility here is bigger than here, right? By the grouping property, we can basically see that this guy has to be bigger than this guy, okay? And that'll be it, okay? Great, so I believe I covered all the homework problem, right? So yeah, please, try your best and do the homework, okay? And they're pretty good problems and they're not that easy, you can see. Okay, so please let me know if you have any questions or comments. Please stay safe and healthy. So I'll see you next time. Bye.